I can start by introducing our last speaker. And first of all, welcome back our colleagues. And here is the first talk in this, also the third talk of our second day, Professor Ming Cao. And I would like to give a brief introduction to him. He got his bachelor and master degrees from Tsinghua University back in 1999 and 2002. After that, he got his PhD degree in Yale University in 2007. He's currently a professor of System and Control with Engineering and Technology Institute in University of Herlingen. He's a fantastic professor. He wins the award from IFAC, and he's also the recipient of European Control Award in 2017. Currently, he's a senior editor of System and Control Lectures and multiple famous magazines, including Talk. His work is inspiring and has lots of nice breakthrough results in multi-agent system and intelligence agents. And let me leave the stage to Professor Ming Cao, and let's start.
Okay, great. Thanks for the kind introduction. First, share my screen. Does it work?
Yes, it works.
Okay.
Yes.
Yeah. Okay. Yeah. Thank you, and thank you for coming to this talk. And today I will share with you some of our research work on using evolutionary game theory into the area of decision making in network systems. And then the game theory and evolutionary game theory, they are very established fields. I just start with how did we come into this area, and what is a control scientist or control engineer may take a different angle to look into such a theoretical topic and find our own way of applying the theorem. So probably you all know that so we are working with more and more powerful sensors, and in particular those robots nowadays, they can move around by themselves and make decisions by themselves, and they become more autonomous. So there's a typical scenario. This is a task for sampling the sea. So the undersea environment is very unpredictable, and we don't yet have a very reliable map of everything that's happening under the sea. So we will rely on different type of sensors and mobile vehicles, in this case, in the water and in the air, and they coordinate, they collect information, and then they share what they have found, and they optimize their actions to take. But then one particular issue pop up, because in such scenarios it's unpredictable, and there's always something unexpected happen. So those individuals, in this case autonomous robots or sensors, when they are making their own decisions, they have the tendency to maximize their own payoffs first, like their lifespan, like how the battery is running, and the safety. So they want to make sure they themselves are safe before they can contribute to the grid, or before they can really talking about collaborating as a group. So we call such behavior of maximizing their own payoffs first. Such kind of optimization actions, we call them selfish behavior, or just self-interested behavior, because it's a need, because we cannot pre-program everything for those agents, and they do have to make the decisions on the spot. And then it is natural for them to be selfish or self-centered or self-interested in order to survive, and later on maybe to contribute to the group and to accomplish a collective task. So then when you have such self-interested agents, so how to make them share information? integrate local information and that get global performance index to be evaluated, and how to handle such an unknown and a changing time-varying environment. So those are the things that as a control engineer, we need to face. It's kind of a new challenge in the new era of applying autonomous robots into more this unstructured, unknown environments. And then coordination, right? So we talk about control, but then in a lot of cases, hard control or programmed controller, as we're used to, are not applicable all the time. So I know in this summer school, traffic and facility networks is a central theme. Just as you have noticed that in traffic systems, if every driver, if they're selfish and they want to have their own shortest path first, and then if everyone is trying to optimize or minimize their own traveling time, but collectively, you might run into trouble. You can have traffic jam. So this is called a social dilemma in the sociology and economics literature. This is a typical scenario. You cannot really control the action of everyone. You cannot not force driver A to take the first action, driver B to take the second action. There's no such facility for you to implement those hard control. And most likely in practice, there can be some soft control in the sense of there's some cooperative actions. I mean, there can be some incentive to steer people from the highly jammed area. There can be different actions. I will talk about this later. But this is one typical example that coordination is a more feasible, or actually the only feasible solution for such social dilemmas. I also want to point out, maybe you haven't realized this, the same idea of coordinating self-interested agents is a very hot and central topic in evolutionary biology. Biologists are puzzled by how those social insects or animals in general, they can evolve into cooperative communities. They can compete for resources, but through evolution, maybe that's encoding their genes, they also have very fascinating collaborative behaviors. So in fact, we engineer, and together with sociologists, economists, and also biologists, we share a common interest to understand or to try to construct the mechanisms to explain and also to motivate those cooperative behaviors in self-interested agents. So the difference from the traditional control of an industrial system in this case is that incentives is more effective rather than to give hard commands. And then there is an evolving process, changing together with the changing with the time, with the social surrounding, with the physical information that is collected over time. So coordination becomes an important concept there. And then just talked about our lab. So we do have a robotic fish test bed. So in this example, this is a short movie, just showing you how we are using autonomous robots, this autonomous robotic fish, to implement such a collective task of removing the obstacle in the middle. So the fish, they want to swim from the left to the right half of the tank, but then they have no idea how heavy that obstacle is. So some of them, they might want to take the job, take the task, but some others might want to wait and even hesitate to take the task. So this shows you one run of the experiment. So there's a fish, I mean, they're all identical, right? But there's one fish, in this case, because of the probability, decide to take the role of the leader. And the other 4 fish decide to follow and to push together. But because I mean, their swimming pattern is not precise, and there are uncertainty in the modeled hydrodynamics of this water tank. So even when this fish want to push the obstacle, he's actually pushing away the other robotic fish. It's counterproductive. But anyway, after some struggling in this task, 5 of them, they did participate in this group task and come to the right half. And then the last fish, it takes some time, so I just stop here. He decided to be a free rider, because if you want to contribute to remove the obstacle, then you need to spend your energy. And then if every fish is selfish, then they want to save their own energy, then such a fish, you can say smart, but it's also selfish. He does not contribute. It's a free rider. So we also adjust the weight of the obstacle throughout this experiment. So then those robotic fish, they have to adjust their strategy over time, right? To be a leader or to be a follower or to be a free rider. And then they will be rewarded if they're able to swim to the right half, and they will be punished if the task cannot be finished. So if you know everyone is a free rider and doesn't contribute, so the task will never be finished. So within 3 minutes, if the task is not finished, everyone will be punished. So this is a typical example of a decision-making process in a robotic system. And then that's a game. So you're making decisions, and the outcome not just depends on your own decision, but also on the decisions of the others. So that's a typical game decision-making scenario. And this can be done repeatedly over time, and then this becomes an evolutionary process. So you can try to see how cooperation might emerge. It's not programmed into them, but they can learn from the others. There's no active communication between the others. Just by observing the behavior of the others, and then try to look into or learn from your past experience, and because this penalty or reward in this game outcome, then you can test different strategies of learning and then try to observe what might be most effective in such a scenario. So that is more or less my motivating setup of what I want to talk about. So we do have this autonomous agents idea in our mind when formulating all the problems, and then such decision maker can be autonomous robots, that's in our lab, but then in different, depending on the application, it can be human, can be animal, it can be sensors, can be a operator of a facility network. So whenever you can, you have a decision-making process that is in a network environment. So some models that I will talk about can be potentially applicable. So by the way, if you have questions, feel free to interrupt me and don't have to wait until in the end. So this is an outline. So I know we have 2 hours. So then in the first hour, I will mainly focus on when we talk about cooperative agents. So what happens, you have also anti-cooperative agents. So then different agents might have different tendencies to cooperate or anti-cooperate. And then, so there's a classical model called the threshold model. I'll explain what the model is. And then for the learning of the decision-making rule, there are also different types of rules, but one very popular and also very intuitive rule is called the best response decision-making rule. I'll explain what it is and make the connection to games. And then we are not just doing experiments or doing simulations. Can we do some mathematical analysis? Can we give some mathematical guarantee for the performance or for the convergence in this case of the dynamics? And then there's one particular model called replicated dynamics. That is a continuous nonlinear dynamical system model. I think a lot of you, if you know, you are familiar with control theory, this can be a very interesting area to work in because this directly point to the paradox of cooperation that biologists are so fascinated with. And then we can also compare different decision-making rules. So like best response versus imitation, how to imitate the best performers. And then we know stability, like the Yapun stability, asymptotic stability, but there's also a notion called evolutionary stability that is a standard term widely used in evolutionary game theory. So I will also explain what that is. Okay. So let's first look into cooperative and anti-cooperative agents. I give everything in a simplified setup just to explain the core concept of this problem. So we think about the decision is binary. So we are not looking into more complicated cases, but start with the simplest case. You only want to choose from one of the two candidate choices, binary decisions. So what is a coordination behavior? So if a lot of your neighbors are taking, if there's a network there, so neighbor means those agents or those decision makers in your surrounding that you can observe their behavior, their actions. Those are the neighbors. So if among your neighbors is sufficient or enough number of them are taking the action, then you will take as well. So we talk about renewable energies. So if in your neighborhood, enough numbers of your neighbors are using solar panels, for example, then you will also use it. So then this behavior of using those renewable energy sources, if that's the action, then your neighbors, their behavior can influence you, and you join them if there's sufficient number of them are doing this as well. So this actually has a lot of this idea, this model of coordinating behavior captures behaviors in different applications. Right now we are in the corona pandemics. This viral epidemics is also a possible one of the ways to model the propagating behavior of the epidemics is using this coordinating behavior. If there's more people are infected, then more likely you are also infected. Then that's a kind of a coordination behavior. And this coordinating might not be the most appropriate word anymore, but you get the idea. And fashion and financial market, this collective decision-making process. Anti-coordination is the opposite. If too many of my neighbors are taking the action, then I will do something different. So traffic jam, that's a very, that's the example in this case. So if a lot of people are choosing the same path, then there's likely to be a traffic jam, then you will choose a different path. So you will not choose the path that most people are going into. And also for communication channels, trading commodities, and there are different applications. So this is rather general idea of capturing the behavior of agents. So what is a threshold model? Threshold is saying that enough numbers are doing this, taking this action. That number, that's a threshold. If the number is crossing a threshold, so you will take the same action if you're coordinating agents. You will do the opposite if you are an anti-coordinating agents. And then in this area, people ask three kinds of questions. So first is, if you have such coordinating or anti-coordinating behavior, will the whole population settle down or on a particular action? So will this change all the time, or there will be a steady state? And then suppose there is such a steady state, the network dynamics converge to, what is the distribution? Can you calculate or predict what is the outcome? And then the third question, if you know they will settle down at a certain particular distribution of actions, how long will it take? So what's the convergence speed? Those are the three fundamental research questions in this area. And the first problem is the most fundamental, but also the least studied. I will show you why this is technically or theoretically challenging to analyze the first question. So those are the language used by people, especially from sociology and economics and biology. But mathematically, if you translate those three questions, they're actually saying, will the network dynamics converge to an equilibrium? And then the equilibrium that's corresponding to will everyone settle down on such a particular action. And then biologically or in economic literature, people ask, will every individual be satisfied with his decision? That's the situation when you reach an equilibrium. So mathematically, we are really looking into the convergence behavior to the equilibrium. Okay, so now a bit more mathematics. Network can be represented by a graph with vertex set and edge set. And then we are considering two-player game because for every edge of the graph, we have two vertices that corresponding to the two players of the game. And then whenever you have a game, you have a payoff matrix. So I'm talking about the symmetric game matrix form. So for two players, because they are taking binary decisions, action A, action B. And then, so if I'm the role player, if my counterpart is also playing A, then I get a payoff AI. So I'm agent I. That's my payoff AI. And similarly, if I'm playing A and he's playing B, I get a BI. So you can put this AI, BI, CI, DI into the matrix. That's a payoff matrix. And then I'm looking at a discrete time model. So then on the time axis 0, 1, 2, 3, 4, every time when the clock clicks, then the game plays, and everyone is playing with their neighbors. And then if you have multiple neighbors, then you just take the sum of all the payoffs you gained in each pairwise interaction. And then I just use NIA to represent I time K. In the neighborhood of agent I, the number of A players. Similarly, NIB of K will be I time K. In the neighborhood of agent I, the number of B players. Because every time you can count the number of people are playing different strategies in different neighborhoods. So now we are taking the sum of the payoffs to be the payoff of each individual. Then obviously, if I am playing strategy A, and if there are NIA, A players in my neighborhood, they're multiplying by AI, that's the first element in my payoff matrix. That will be my payoff against all those A strategy players. And then BI multiplying MBI, that will be my payoff gain from my B playing neighbors. I take the sum, that will be my payoff when I'm playing strategy A. So you get the idea. You can calculate, right? So if you're playing A or B, and then you can compare what is the possible payoff that you are getting. So then what's best response? Best response means you compare if I'm playing A or I'm playing B, which one will give me a higher payoff? So I'm selfish, I'm trying to optimize my own payoff. I always pick that action that is giving me higher payoff. So that is the best response. I'm best responding to my surrounding agents when they are playing different strategies. So in the special case, when the playing A and playing B doesn't make any difference, then so you can fix to either A or B, or there's some special rules. That's rather the special case. So that is the game setup. So you are maximizing your own payoff because of the pairwise interaction, the game interaction. You can imagine, right? This over time, every time everyone is best responding to the surroundings, and then there can be change of strategy over time. And then you ask, okay, will everyone change their strategy forever? Or in the end, everyone will be converging to a strategy, and then the network will settle down, will be at the equilibrium. But before we are going in that direction to the analysis, I just want to make the connection with the threshold model, because threshold model, that's people, they understand that such network dynamics. There is certain threshold in the neighborhood. You either are coordinating or anti-coordinating in your neighborhood. So just to make that connection, I reparameterize those payoffs. So I'm introducing tau I to be the ratio between gamma I and delta I. And gamma I and delta I, those can be computed by the payoff matrix. So in fact, so I can rewrite such a breadth response rules that is on the bottom to the thing on the top. So I'm comparing the two payoffs. Is actually I'm comparing, right, the number of A-plane neighbors. Is that greater than or less than a threshold or not? That threshold can be calculated as tau I, that's parameter tau I, multiplying the degree, the number of your neighbors. So in other words, from a game theoretic approach, look into this dynamics, you are using the best responding updating rule. You're comparing the payoff. But from this cognitive point of view, so I'm a coordinating agent, I'm comparing with a threshold. That is my cognitive decision-making rule. Actually, they're equivalent. So you gain this insight. Okay, so these two ways of thinking from different fields, they are actually the thing. By looking into the best responding rule, you can recover threshold models. So this cognitive threshold model actually is the mechanism of best responding in a game setup. So that's the first point I want to make, right? The models from different fields, you can actually make connection. And then when they share the same features, you can apply your analysis to these models. And then, so this anti and coordinating agents, they are actually different versions of this threshold models. But then, sorry.
Sorry, the graph of the system is assumed to be static, or it can be dynamically evolved.
Right. So because in this updating rule, just only look at the time at the moment. Right. So then, for now, that's a decision-making rule. But then, for the next time instance, for decision-making rules, certainly it can be applied to the case of time-varying graphs. But as you can imagine, when you allow the graph, the network structure to change over time, it will make your analysis more difficult. But then the model itself can incorporate that time-varying case.
Okay, and in this model, the state of the system at time step k+1 does not depend on the state of the system at time k, right?
No, so they're independent from each other.
Okay. Okay, thank you.
Okay, thank you for the question. And then we look at the analysis. So the research goal is that we want to look into the dynamics of the network. Will this converge or not? I'm introducing this notation. So plus means so tell that's a threshold. But then I'm to give the version of analysis, I look at a simple case when everyone has the same threshold. So I will relax this in a minute. But first look at the case when everyone has the same threshold. That's a homogeneous case. And then plus means everyone is a coordinating agent. Again, it's homogeneous. Everyone are coordinating agents. They will do the same when sufficient number of neighbors are doing the same thing. And minus means anti-coordinating agents. So they will do the opposite of their neighbors, the majority of their neighbors. And plus and minus, when you put them together, that means you have a mixed population of coordinating and anti-coordinating agents. Those are the three different cases of the mixture of the population. So there are three cases. You have pure coordinating agents, pure anti-coordinating agents, or mixed coordinating and anti-coordinating agents, and to look at the convergence of the dynamics. To just show you an example, right? So this case, everyone had the same threshold 1/2. So, so you can, so then there's circle A and B. So if there's an empty circle, means that agent is taking action A now. If it's solid circle, means it's taking action B. And this blue circle means the threshold is violated. Right? So you look at your surrounding neighbors, you count the numbers, and then this is coordinating agents means that you will take the action of the majority of your neighbors. Right? So that is an example. So if that's the initial condition, you can tell that all those blue circles indicating those agents, their threshold is violated. So if you look at the upper left, his majority of the neighbors are taking action A, but itself is taking action B. Right? So then in the next time instance, if this agent is activated, then he will switch his action to action A to follow the majority of the neighbors. So in this case, I'm doing the asynchronous updating sequence. So every time there's one agent that is activated and following this best responding or threshold decision-making rules to switch actions. So if that's the first one, he will switch. And if that second one, it's also switch, and so on. Right? So then you can do the simulation over time. I just skip the middle steps. And in the end, in this run of simulations, with that initial condition, with that particular updating sequence, the upper three will take B action in the end, and then the lower half of the network, or more than half of the network, will take action A. And then it will stop there, it will not change anymore. So it does converge to this case. So then that's an example when things will converge, but there are also things, situations that they will not converge. So one simple example, you have a mixture, one coordinator, one anti-coordinator. So suppose your initial action is A and A. If you acted the second one first, because he's anti-coordinating, he will become B player. Now, if you activate the first player, because he's coordinating, and then he will become B. So you have A, B, now you have BB. If you again activate the second one, you have BA. The first one, you have AA. So then you come back. So you have a periodic solution coming up in the network. That's one example. You can see oscillation, periodic behavior in the network. This will never reach an equilibrium point. You have a cycle there. And also, if you have synchronous updating sequence, right? You have two, in this example, you have two anti-coordinators. Their initial value is A, B. And if they're synchronized to activate together, because they're anti-coordinator, they're perfectly fine now. So you have AB, they will remain AB. If they're BA, they will remain BA. However, if they start with AA, then the next instance it will become BB, and the next instance become AA. Again, you will see cycles here. So depending on how you activate them, synchronously or anti-synchronously, or the initial condition also plays a role in this. So they're really very rich behavior, but can you really expect that convergence to equilibrium can happen, always happen, under some conditions? Mathematically can prove this fact. And the answer is yes, surprisingly. So then I give you one result here, saying that if you have a pure population of coordinators, and you have asynchronous updating sequence, namely every time there's only one agent get activated, then no matter what's the updating sequence you are looking at, but if you fix the network structure, but you don't care what the network look like, they're very regular or they're very sparse or very dense, you don't care about the network structure, but then they should be fixed, as someone asked in a minute. Then you can always guarantee the convergence to an equilibrium point will take place in finite time. This is rather surprising result. People have worked on a threshold model for years, decades, and then so this result from our group was quite a surprising result to some people. And of course, so then this pure strategy Nash equilibrium. So because I think you know what a Nash equilibrium is, you have heard about it in the game. So if you are at the Nash equilibrium, then no player has a tendency to deviate from their current choice of strategy. That's a Nash equilibrium. And pure strategy means they're not using probabilistic way of choosing their strategies. They rather have a deterministic way to choose their strategy. That's a corollary I will not go into. But you know that if you want to know more, feel free to contact me afterwards. And then similarly for anti-coordinating agents, if you have a pure population of anti-coordinating agents, you can have a similar convergence result. But then, so how to do the proof? That's the key. So if such a result is surprising, and then why is it difficult to prove, or for someone it's difficult to prove? So then I just gave the rough idea, and then I give you the reference. You can read our paper if you want to know more the technical detail. So there's a potential function you can utilize. So we prove everything for the case when everyone had the same threshold 1/2, just as you see in my first example. So everyone has the same identical 0.5 threshold, and then use a potential to show that this converge. That's the first step. And the second step is that for all those networks, when agents they really differ in their threshold, you can build a augmented network. It's more like a transformation. You can transform a network with heterogeneous threshold into a network with a homogeneous threshold of 1/2. So there's one particular construction step we can do to do the transformation between the two scenarios. And then, so because of that existence of the potential, and then you show that whenever there's a change of strategy, then the potential decreases. And following similar ideas for the Lyapunov analysis, you will show the convergence. But the potential works for a homogeneous network with this 1/2 homogeneous threshold. This can also carry over to the original network when the agents differ in their threshold. So that's the rough idea in the proof. So what is the potential? That you can see the really boils down. What is the potential that one might use in the Lyapunov-like proof? So then this potential is for every agent you can sort of, let's say this is an A-plane agent. That's for every agent you can define what is the maximum number of its A neighbors that it can tolerate. Remember, we are doing the anti-coordinating case, so they can tolerate up to a threshold. If you reach the threshold, it will switch to the different action. And you can compare how many A-player agents, A neighbors you have with the maximum number that you can tolerate. There's a difference there. And then that is the thing for each individual agents. And if you take the sum of all of them, that gives the potential for the whole network. And then you can show that if you take that as the potential for the whole network, it will decrease by at least 1 whenever there's an agent switch their strategy. So then this gives you the analysis. So if we're not going to this, there's some also part why it's a finite steps. That's also part of the proof. But I will not go into detail given the time. And then this is a construction of the augmenting agents. So going from this original, so this is a case when you have the threshold 1/3, and if you put in some additional, we call it virtual agents, and then they call this Y structure there. So A, B, B, you add this to the original, then this new network, then this agent I will have a threshold of 1/2. Okay. And then your added part, they will never change their decision because of the 1/2 threshold. So then, so I'm just putting this 2 figures here, and then you can spend more time if you need more time to think about this. So by adding this Y structure part, ABB part, to the original network, then you can modify, you can change every agent, their threshold from a to the heterogeneous threshold into the homogeneous 1/2. That's the construction. Little trick you can play in the proof. So that's the proof of this. And then the finite time convergence, the finite time, the bond is bounded by the total number of edges in the network. That gives you the convergence time analysis. So that's the overall theoretical result you can prove, like given you a network, and then you can show guarantee the convergence. But then there's some technical conditions you need to have this convergence. If you violate these conditions, what happens? There's asynchronous updating, that's very important. But sometimes you can allow the agents to do partially synchronous updating. So I will not go into this, but just if you want to know more, we can discuss offline. So there's a way to relax this requirement for asynchronous updating. And then that can still give you convergence, but then it will be a convergence probability one. This is a probabilistic convergence. So that is a first part of the talk. So then just about this cooperative and non-cooperative agents. And then I just show you that indeed, given a classical model, if you know some more about the opponent theory, you can prove mathematically some surprising results that you cannot just by looking into cannot obtain by looking into the simulations or the experiments. So then what I will do now is to go deeper. Right? So if we know this mathematical analysis is useful, can we do more? Right? And then what I will talk about is this replicator models that's very popular in evolutionary biology or evolutionary game theory in general, and then to see how we can do some more analysis using dynamical system theory. So we talk about cooperating agents and anti-cooperating agents already. Let me just emphasize more. This cooperation that we take for granted for our robots or for us as a helping person in our nature is really a paradox in biology. If you think about what Darwin says survival of the fittest, because competition, that is, will cost energy, cost time. And then if someone is really want to be the fittest, then why should he or her contribute to the cooperative behavior of the group? How does he or she to overcome this tendency to be a free rider? Because in the end, those benefits will be distributed in the group. Right? So everyone can benefit from the success of the group task, irrespective of whether or not they may have contributed or not. So that's called a paradox of cooperation. Cooperation or altruism, that's a evolutionary puzzle. So if you, I talked about two-player game in a few minutes ago, but then also you can talk about multiplayer game. That's called a public goods game. Right? So public goods that is enjoyed by everyone. But then why should individual they contribute to this public goods? So then the erosion of the public good. That's also kind of explain why this cooperation can be a puzzle to see why this is happening. And then Science, they have ever put up the magazine. They put a list of all the questions that are of the list that is challenging across discipline, and this cooperating behavior. How did that evolve? That's one of the top questions in the list. It gives you a sense that not just our control people, or not people working on game theory or cooperative control. In general, that is a very big, interesting scientific question to attack. So in science, I mean, people, they have this biologist give different mechanisms. There's, for example, network reciprocity. So I do something for you, you do something for me in return. Right? That's those kind of rules. So very rich theory. But then maybe for each different animal groups or each different community, you have to come up with different theory. But then can we have a more general theory in the end? So just let's look at this Prisoner dilemma. I'm sure you have all heard about, but I just want to look into how this can go into a more interesting mathematical dynamical system modeling out of such a simple game. Again, it's two-player game. The payoff matrix corresponding to the cooperative and defective behavior. Two cooperative or not two cooperative. But if you have two if I'm cooperating, you are cooperating as well. So I'm the role player, you are the column player. So if we are both cooperating, we get the benefit, but we share the cost C. So B minus C will be the payoff. But if I defect and you cooperate, so I can take advantage of my counterpart, I get the whole payoff B. So if I compare the two, if I know my counterpart is playing cooperative, then I will be defective because B is bigger than B minus C. And then if my counterpart, my competitor, he is to defect, then I'm comparing these two payoffs minus C that I'm being taken advantage of, 0 if we are both defecting. Again, 0 is bigger than minus C, so I will be defective. So then you probably heard about this. In Prisoner Dilemma game, to defect, that is a dominating strategy. And then there's a mutual defection, that is a Nash equilibrium. I explained the Nash equilibrium just now. And then although mutual cooperation, B minus C, is more profitable, but in the end, we are trapped in this mutual defection situation. Okay. And then, so that's two-player situation, but people also generalize this into networks, and then they even talk about chaotic behavior. If you look at the patterns of what might pop up, the different color means cooperating or defecting agents, and they can be called spatial chaos. It's really very complicated, rich behavior, sometimes not so easy to analyze. And then, so people are looking for theory to look into such studies. And then John Maynard Smith in 1973, also published in Nature, proposes evolutionary game theory. In this case, you still have matrix game. I have explained to you this two-player game. You have payoff matrix. But then in the general case, you might have M different strategies for each player. And then what is a mixed strategy? I talked about pure strategy already, the deterministic. So pure, the mixed strategy means with probability P1, you play the first strategy and so on until you have PM to play the M strategy. So this is a probability vector. So with probability, you are using different strategies. That's called a mixed strategy. And then if you just try to make it easier to understand, give this illustration, if you have in the three strategy case, so then if you are having deterministic strategy, that corresponding to the unit vector along the axis. So with probability 1, playing this strategy in this Z direction, that's X direction, Y direction, each unit vector corresponding to a deterministic strategy. And then this shaded triangle, each point corresponding to a mixed strategy. That is with the probability corresponding to the coordinates in such a three-dimensional case. In 3D, everything can be visualized. Once go to higher dimensional space, then things are more difficult to be visualized. But anyway, so the strategy space in this case is very intuitive. That become a triangle with a shaded triangle representing the space. And the payoff, because that you have a payoff matrix, then actually that becomes a quadratic form to calculate the payoff. So you have a strategy P, that's a mixed strategy for the first player, and then the counterpart is playing strategy Q, that's another probability vector, and then a two vector, and then if they multiplying this payoff matrix, so P transpose is a row vector, and Q is a column vector, and this quadratic form will give you a number, scalar, that will be the payoff. So then in such a matrix game, in this case, the payoff can be very committedly computed by the quadratic matrix form. And then there's some technical conditions, I will not expand here, but just if you have a very large population, a very well mixed, everyone has a chance to interact with everyone else, and randomly can pair up people, and then every time, so if they have a payoff, and then there will be more people in the biological explanation, it would happen evolution over time. So if at a certain time, one strategy player is having higher payoff, then the next time instance, there will be more players playing the same strategy. They call it reproductive rate. Right? So the better performing players will have more offspring over time. Or if you, from this rational decision-making point of view, so then more people will imitate the best performer. But then the consequence is the same. Right? For some strategy with good payoff, you will over time you will see more people adapting that strategy. And then there's under those technical conditions, you can actually write down a replicator equation. So what does it mean? So I means the I strategy. Xi means in the whole population. Now remember, we have a very large population. In that whole population, the share, the percentage, or the ratio of people who are using strategy I. And then the rate of change of the people who are using that strategy I will change over time because that's a continuous time model. But then what determines that rate of change? First, the current share. The more people you have for now, then you can change it more faster in the system. But it also depends on the second term here. That is the comparison of the people, of the payoff of the strategy I player with the payoff of a average player in the population. If the payoff of strategy I player is higher than the average payoff in the population, then this becomes positive, then the share will increase. Otherwise, the share will decrease. So this replicator dynamic boils down to the idea that compared to the average performance of the payoff in the population, relatively you're performing better or worse, and then the share of this player will increase or decrease. That's very intuitive, easy to understand concept for replicator dynamics. But then if you mathematically, if you look at such an equation, you realize that that is a nonlinear system. Right? And then, people look at, oh, that looks very intuitive, and can we draw conclusions to predict where the system to evolve to? Remember, the fundamental question we are interested in is to give a long-term prediction to see where the system will converge to. So what some people might want to say, okay, Nash equilibrium, because that's a situation that people will settle there. So then they say the replicator dynamics will always convert to a Nash equilibrium. That's very nice. And then in this model, the Nash equilibrium actually corresponding to this inequality. Right? So if you are at the Nash equilibrium X star, X means the share of the population. If that's already at the star or the equilibrium state, whenever that population share deviate from the star, it will result in a lower payoff. So then there's, for that reason, the population will stay in that equilibrium state. So that definition of a Nash equilibrium in this context is appealing because when you get such a replicator dynamics, there's no assumption about rationality. People simply follows the reproduction way of evolving in a biological way. But then if that turns out to always convert to Nash equilibrium that's corresponding to the rational thinking, then you can build a bridge between biological evolution and rational thinking. So that's why such a claim is so tempting, so appealing to people. But that's not true, unfortunately. And then another tempting claim is that called this evolutionary stable strategy. So what that is, so because the equality for Nash equilibrium has an equality sign there, right? So then if you look further, if that state is a Nash equilibrium state, but in addition, if the equality sign holds, then you have to make sure that additional inequality applies. So this actually says if there's a mutation in the system, and then the X star will be strong enough to eliminate mutation in the system. So if X star for some reason mutated into X, then this has a tendency to come back to X star. So that is why it's called evolutionarily stable strategies. So another tempting statement is that if that converge to interior equilibrium, that will go into a ESS, evolutionarily stable strategy. That's also not true. But how do we know? Right? Those are so appealing to claims, they're wrong. Right? They kind of make sense to people. Right? There's some rationality and biological reproductive processes, and this evolutionary stability corresponding to a converging process. Right? But why are they wrong? Just give you this example.
Excuse me.
Yeah.
Is there any claim about the uniqueness of the equilibrium point, or?
You mean the correct one?
Yeah.
So then I would say why they're wrong first, and then I will tell you what should be the correct version of the conclusion. This will be more restrictive. So these two claims are too general, but then the restrictive version of them can be correct. But then I will show them in a few slides later.
Okay, thank you.
So just give you the counter example of those two claims. So you can check such a game. You can also check the Nash equilibrium in the game. So in this case, that's in the middle, that part. So that's the Nash equilibrium. And then you can check that. So in this case, this is almost globally asymptotically stable system. So because whenever you are in the interior, you will converge to this point. You can check that the dynamical system result. But then this point, although that's Nash equilibrium, but that is not ESS. That's because there's a very special way of perturbing this equilibrium that is along the direction of E1. So in the first strategy, if you perturb your system in that way, it will violate the ESS definition, the inequality over there. So in other words, you do have a almost globally asymptotically stable Nash equilibrium in this case, but that not have to be a ESS strategy. But there's a gap between these two concepts. And then you can also look at the system when you take the inverse of this matrix. You can imagine the payoff matrix, when all the payoff are having the opposite signs. And then in that case, you just reverse the trajectory of the system. The trajectory will convert to the boundary of the system. They will also not convert to the equilibrium in the middle. But it tells you that for a game with this dynamics, they do not necessarily have to convert to an equilibrium. In this case, it can convert to the boundary. So those are the examples that is a counterexample to the claims just now. So then what should be, just as Shimon Sadas has asked, what should be the correct statement? The correct statement should be that if you know X star is ESS, then that if and only if for all the X near this X star, the inequality is satisfied. And then you can see the other way around. If you know it's already an ESS, then you can claim that it's locally asymptotically stable. So those are, and also if you know it's interior ESS, then it is almost globally asymptotically stable. So those are always starting. If you know that is ESS, then what can you say more? Right? That's, but not the other way around. So then for the first result, you can check the reference I'm giving there. And also more importantly, there is a Lyapunov function, as you have seen in my proof in the previous problem. Lyapunov function is very important. And this does have a very special form in this case for the Lyapunov function, which can be convenient if you want to build controllers later on for the problem. That's what I want to tell you. It's a strict local Lyapunov function. And then what converts to this actually called a heteroclinic cycle. In case you know some dynamical system theory, then that is the terminology people use to describe the convergence situation in this case. So what we have done in our group, we further developed this Poincare-Bendixson theorem and clarify further in different scenarios. You count the number of equilibrium in the middle or on the boundary, then you can classify different situations. When will it convert to a fixed point? When will it convert to a closed orbit? And when will it convert to a heteroclinic orbit? So our group has done some work. So given the time, I will not go into detail, but then we can use dynamical system theory for such models built upon the previous existing work. We can look further into the possible scenarios. So I will not give you the detail of the results in the talk, but the different scenarios you can predict the trajectory of the system. So in this first hour, what I have done is that I gave you two models, one discrete time, the other continuous time, but they both rely on kind of Lyapunov function analysis, can give you the convergence, long-term convergence predictive results with mathematical guarantee. So what I will do in the next part, I will build upon such results and then look into can you introduce control? But if you know the convergence, then the idea is can you introduce control into this? And then we will talk about incentive-driven control and how to introduce incentives into system to build into this the system model. But I just want to say that if I know some of you are working with power grids, with communication networks, with traffic networks, such an idea of looking into how the agents, when they are cooperating or anti-cooperating, and then there's a decision-making process in the system, and then this game idea is very relevant. And I will go into control in the next part, but then as you will see that a lot of the results are still very preliminary and calls for more work in the area. So we'll go into more in the second part. I just gave you a rough idea for now that is still a very open area and a lot more questions can be worked on. So for this part, I gave you some of my the references because I didn't give you all the technical details. So there's a review paper, the third one. So if you want to know the historical development and then the summarizing the different results, the review paper from our group, that may be something to look at. And then because I didn't didn't give you the construction of the proof for the first problem, this threshold model. The last paper gave you, especially the supplementary material in the paper, gave you the details of the proof. So you can feel free to read them, and if you want to discuss more, and you can contact me. So I suggest we take a 5-minute break, 4:40. So in 5 minutes, we come back again and we go to the second part. So see you in 5 minutes.
Professor Ming Cao, there is questions in the chat.
Okay. Right. So it's probably difficult to define those thresholds because then I mean that's possible. I'm just because you can define for each, if you have more than two strategies, then for each strategy you can define a threshold, and then you say if that crosses threshold, then you take certain actions. I think that's perfectly fine to have more than two. I'm just thinking about the proof because the proof we do have this potential function that is corresponding to the difference between the numbers comparing to the large allowable, tolerable. Right. So I'm not sure the proof, but the similar conclusions can be carried over. But I'm confident that the model can be built for the more than two strategy case. Okay, we are back, and let's just continue with the story. The first part I showed you convergence. I mean, you can predict, given the model, the long-term behavior of the system, especially convergence to equilibrium. That is of very important consequences when we are designing controllers or we want to manipulate the dynamics. Then we know there's a hope that we can shift the dynamic to a certain equilibrium that we prefer or we desire. So I'll continue with the story. So then, especially learning become important, and then feedback control is in a sense it's kind of feedback into the system. And then how can we build those things also into the model? So let's take another look at this Prisoner dilemma problem. I just gave you in the first part. I said that this to defect, that's a dominant strategy. So no matter what your counterpart is playing the strategy he's choosing is always more rational to defect. Then there's a free rider problem. So everyone in the end becomes a free rider to defect, doesn't want to contribute to become a cooperator. So this is a classical setting. I think everyone, when they talk about game theory, they probably knows about this prisoner dilemma game. But nevertheless, there can be a twist to this classical problem. That is, will the players, they behave differently? They will not be the defector anymore if the game is repeated. So then in the last part, we already talked about the replica dynamics. That's kind of already telling you that if as time evolves, the dynamics can take place, and then there's more things can happen. But then just look at the simple form of the game. The most well-known form of the game we know, the prisoner dilemma game. Can we already observe something different if you allow things to take place repeatedly over time? Can people learn to cooperate in this case? I'm showing here a piece of movie that is from a documentary made in 1986 by BBC. So Richard Dawkins, you probably heard of the name before. That's the author of the book Selfish Gene. And he is giving this scenario. So that's a prisoner dilemma game. So you probably recognize the payoffs, C and D corresponding to cooperate to defect. And those are the payoff matrix you'll see. And then there are two players, they will play over time. And let's just see a clip of this documentary and to see what can happen.
Right, now you both know what the rules are, Adrian, Anita.
We invited Anita and Adrian back to play the prisoner's dilemma game. This time, repeating the game an indefinite number of times, more like a relationship in real life.
No. Adrian chose D, Anita chose D, so Adrian gets 2 points, Anita gets 2 points.
Could they use the successive moves to build up a mutual strategy for cooperation, not defection, and profit by it?
Right, make your second choice now. Adrian chose D, Anita chose D.
But it's a bad start, mutual defection.
Right, think about your third choice, and when you're ready, let me know. Right, make your third choice now. Adrian chose C, Anita chose D, so Adrian gets 1, Anita gets 4.
At last, a cooperative signal from Adrian. What will they do with it?
Choice. Right, next choice now. Adrian chose D, Anita chose D, 2 points each.
No response from Anita, and Adrian has fallen back to defecting too.
Choice. Next choice now. Adrian chose D, Anita chose D, 2 points each. Right, ready for your next choice? Right, make a choice now. Adrian chose D, Anita chose D, 2 points each.
They've got locked into mutual defection.
Now. Adrian chose C, Anita chose D. Adrian gets 1, Anita gets 4.
Adrian signaled again, but no luck. It's as if he were relying on telepathy. Is there any way we can work out in advance what the best strategy is? Computers can be programmed to do anything you like, and that includes playing the game of prisoner's dilemma. All you have to do is to feed in the right program. One program for playing the game, another program for playing the game, and they can play against each other. But that's just 2 programs. We need to increase the number of programs that we play against each other in order to find which is the one that will succeed best against all comers. And that was the idea that occurred to an American political scientist, Robert Axelrod. He advertised in a learned journal and invited professors, experts in game theory to submit programs that they thought embodied the best strategy they could think of for playing the game. He then gathered together all these programs for playing Prisoner's Dilemma, played them off against each other in a computer to see which would win. In other words, he organized a computer tournament. He got altogether 14 entrants, all sent to him as computer software. This one was especially interesting to me, Friedman. It was just like my grudger. Cooperative to start off with, but a permanent retaliator once cheated against. Although this program appeared cooperative, it wasn't. It kept trying to sneak in with the occasional out-of-the-blue defection. And Downing relied on its cleverness, constantly updating the statistical chances of cooperation or defection from its opponent. But it always started pessimistically, assuming the other player was going to defect. And the simplest program of all, tit for tat. It started with a nice cooperative move, and thereafter simply copied what its opponent's last move was, playing a C for a C and a D for a D. Nice means never the first to defect. The computer played them all off against each other. When the results came out, he got a surprise. Tit for tat, the simplest program, had proved the best. Axelrod published his analysis of...
Yeah, I'll just stop here because it's a long documentary. You can look for this online to see the whole documentary if you want. It's a very interesting discussion about cooperative behavior and the connection to game theory. And then, as you can see, if we play the game repeatedly over time, and then you allow the players to look back into what happens and then to update their strategy and to learn the behavior of the opponent. And then there can be different strategies, even probabilistic strategies that can be compared or compete against each other. And then tit for tat, I mean, this documentary at that time, that's already 20 years ago, and then that pop up to be a very successful strategy for such repeated PD games. So what I will going to present is that after these 2 decades, what is the new progress? And then even for these classical games, are there still anything surprising? And this is a zero determinant strategies that's discovered a few years ago that shows that even for such game, we think we well understand them. There's still a new twist people can introduce. That is single-handedly, some player can manipulate the payoff of both of the 2 players. That's the first part. And then for the feedback part, I will give you an example of 2 population with environmental feedback. So then for the replicate dynamics, not just one population playing the game, but if there are more than one population, what happens? And then that is just pointing to this control part that I mentioned a few minutes ago. So let's revisit this so famous, so classical Prisoner's Dilemma game. So we just give the RSTP to make it more general. So R means reward, S is sucker's payoff because you're being taken advantage by the opponent. T is temptation, try to take advantage of the opponent, and P means punishment. The case when mutual defection is the outcome. And then, so let's try to think about this repeated game over again, over time, what happens. We can, so if those players, they're allowed to play the game probabilistically, with certain probability they choose to cooperate or not. Just as you in the movie you have seen, Adrian and he's trying to switch between C and D, and there's some probability he's switching to be cooperative. So then let's say that if those 2 players, they have certain probability to cooperate, and that is fixed, probability. Then every round of the game, there are possible 4 outcomes. The combination CCCDDD and DD, and each of them, they will corresponding to a probability that determined by the probability of the 2 players. And then you can define. So if I'm the player 1, so if I have seen CC in the previous round, then next round, if I choose C, that will be my P1. And if I see the other scenarios, I can also determine the probability I will cooperate in the current round. In other words, my strategy in the current round to cooperate can be represented by these 4 numbers, 4 probabilities, each corresponding to a outcome in the previous round. So I call this probability P, right? That's a probability vector. And then analogously, right, in the same way, my opponent can also be represented, the strategy, by the probability vector Q, also has 4 number in it. So those are strategies. Then I can see how the system evolves, right, from time 0, 1, 2, 3, 4. In fact, at every time, there will be 1 outcome, right? And I can build a state transition matrix. So I can calculate if the previous round, the outcome is CC, what is the chance that I see CC in the current round? Right? That is determined by the 2 players strategy, P and Q vectors. So give you P and Q, you can calculate such a state transition matrix, telling you the outcome of the game over time. So that's perfectly reasonable. But what is more interesting, I mean, we all are familiar with the linear algebra case of the Markov chain calculation. If you are given a state transition matrix, then you can ask yourself, under some conditions, for such Markov chains, there will be a steady state distribution. So that steady state distribution corresponding to the left eigenvector of the Markov, this state transition matrix. But give you the P and Q, you can calculate the matrix M. Now further, you can calculate the steady state distribution. So then you know in steady state, what are the chances of seeing one of those 4 outcomes? Okay. And then, so once you can calculate that steady state distribution of the outcomes, you can further compute the expected payoff. So if I know that steady state distribution, then I know the chances I encounter C or D players, and I know my probability vector, then I can calculate my payoff. So I'm not going into detail, but then you can calculate this offline if you want. So the payoff of the first player as S1 can actually be written as the determinant of this 4x4 matrix. It looks interesting because the last column that are completely determined by the payoff matrix RSTP. Okay. And similarly, you can calculate the second player S2. Right? It's also a determinant of a 4x4 matrix. But what is even more interesting is that if you can calculate the expected payoff S1 and S2, you realize that S1 and S2, they are dependent. They have to satisfy certain relationship to be more specific. So if I give this alpha, beta, and gamma, those are just constants, then this alpha S1 plus beta S2 plus gamma can be written into this determinant. And what's very special is that if you look at this 4x4 matrix, the second column is completely determined by agent 1 strategy, by the P vector. P vector determines the second column, and Q vector determines the third column. And then because that's a determinant, right? And we know that the determinant will become 0 if the columns are linearly dependent, or in the special case, because I have the full control, because I can control my p-vector. That's my strategy, making my choices corresponding to changing the p-vector. Because I, as a player, I can completely determine the second column. One possibility is that I make my second column equal the fourth column. The fourth column is determined by the constants and the payoff matrix. If that's the case, then determinant becomes 0. Then I know S1, my expected payoff, and S2, my opponent's expected payoff, has to satisfy such a equality. And to make it even more special, if I pick alpha equals 0, I can force the expected payoff to be the opponent to be minus gamma over beta. This is like a ball, right? So if you have studied PD games, prisoner dilemma games for such a long time, suddenly you realize that if this can be played over time repeatedly, and people are using this probability way of playing the game, then unilaterally, so I as a player, single-handedly, I can force the expected payoff of my opponents. So if I'm smart enough, so I can notice, I can calculate this determinant. So this is a very surprising result, saying that even in such a game, unilaterally, there might be manipulate the outcome of the game. So this is interesting for our control people, right? So we are introducing a certain learning strategies as an algorithm try to shift the game outcome. But this is a new way. So just some basic linear algebra, then there is such an algorithm you can implement, and then you can control the outcome, the payoff of your opponents. So of course, so there's assumptions, technical discussion. There are details there. Since they're not that simple, but then anyway, this gave you a new direction to think about working on controlling the outcome of the game. And then if you are familiar with this theory of mind, right, then you are just assuming other people are doing things in this way, right? You're having this model in mind. That's a big assumption. So if you want to check more details about this prisoner dilemma, the first paper that's appeared almost 10 years ago in PNAS, so you can check the computation there. And our group, we have done extension of this theory determinant. Now we are really on purpose introducing this theory determinant strategy for multiplayer games, and then different network structures. And then the algorithm becomes more complicated. And then the final expression is not as neat as what you see in the two-player case. But then there's still a way to introduce control action using theory determinant strategies. So I will not go too much to detail there, but just I will give you the reference from the working number group in the end, because I want to expose you to more ideas of introducing control. The second idea to introducing feedback is called environmental feedback. So what that is? So remember that I have covered this replicator dynamics in my first part. Right? So the share of a certain strategy players will change according to the relative performance. Is performing better or worse than the average player in the population. Right? That's the replicator dynamics. But then, so people have worked on Nash equilibrium of the game, evolutionary stability of the game, and also what is optimal. Right? So if you are at a stable equilibrium, is it optimal for the players, or for one particular type of player, or for all the cumulative payoff of all the players? There are different topics have been studied there. We have summarized that into our survey paper. But then another extension or the way to generalize the model is that because we talk about tragedy of the commons, so that means if everyone is a free rider, is eroding the public goods, and then it will become miserable for everyone in this collective. But can you explicitly build in your model that feedback? So if that public good is depleted, can you build that into your model to express that, to describe that? So that is, we have this closed loop system. There's a population dynamics that's playing the game, just like the replicator dynamics you have seen in the previous slide. But there's also a environmental resource. They can change over time, and this can counteract. Right? This is giving you feedback into the game playing population. So that is a model we call the evolutionary game models with environmental feedback. And in this case, all the payoff matrix will be parameterized by a R parameter. So R means resource, the resource in the environment in response to the population state. So how many people are cooperating, how many are not. Then the resource in the environment is growing or decreasing. And that R, change of R, will be explicitly shown in the payoff matrix. So then the payoff will get bigger or smaller, corresponding to the resource in the environment. So that's called the environment-dependent payoff matrix. That's first introduced that's 5 years ago in another PNAS paper. And then, so we call this co-evolutionary game dynamics. So not just the population playing the game is evolving, but the environment is evolving with time, with population also. So that is called co-evolutionary dynamics. And what we have done even further is that we introduce multiple populations. So think about if you have robots, then they can be different robotic groups. Or if you are using energy power networks in this evolutionary setup, you can think about different type of energy sources. People are relying on different companies, or they are having different ways of using the energy. There are different populations, and then there can be interaction between different populations, and that will also affect the game dynamics. So then there's an evolution of the population, and there's also the evolution, co-evolution between the population and the environment, and then the model becomes more inclusive. So just give you the example. I give you the rough ideas, and then you know what the directions we are heading. Which we look into the two population case. And again, you have those strategies, but then you have two population. Now you're generalizing from the single population case. You have a single replicator dynamics set of equations. Now you have two set of equations. For each population, you have a set of replicator dynamics. So you can look at in each individual population how the share of different strategy players are changing over time. And in addition, the payoff matrix are parameterized by the environmental parameter R. In this case, so in our paper, because we want to have analytical results, this dependence of the payoff on the environment, we give a linear relationship. So the linear R enters the matrix linearly. And then there's we call this a logistic model for the resource. So you can see the resource is also a variable between 0 and 1. 0 means fully depleted. 1 means at the maximum. And then this always changes between 0 and 1. And then H tells how the environment is dependent on the population state. So if the players are more cooperative, then it will make the resource to grow. Right? So that is reflected by this H function. And then to be more concrete, right? So we have given a very specific form of the H function in our paper. This H just simply you put together we call it enhancement strategies and the degradation strategies, and we put them together into the H function. Again, that's a linear function, just to make things easier to analyze. But nevertheless, the technical details are less important. But then the key idea is that you are able to, if you do this in this way, to build a model with the replicate dynamics for each individual population, and together with a coupled environmental dynamics of the R parameter. And then, of course, you are looking at a higher dimensional dynamical system, and then the analysis becomes more complicated. So the question is, can you still drive at some specific analytical results in this case? So just to show you an example, to show how the results might look like, we look at the special case. Again, that's a prisoner dilemma game, right? So then the payoff matrix of the populations corresponding to the convex combination of PD game, the prisoner dilemma game, and then they are reversing the first row and second row of the PD game matrix. I just gave you the counter, the opposite effect of cooperating and defecting. And then the convex combination gives something in the middle. In the two extreme is described by the PD game matrices. And then what happened is in the middle, there's a convex combination of the two extremes. And then, so then that will give you, then once everything's set up in this way, then you're ready to look into the analysis. What can be said for the long-term behavior? But before I go into the technical proof, just gives you some intuitive idea through simulations. So because we have X corresponding to the state of the first population, Y corresponding to the state of the second population, and R corresponding to the environment. Because we are looking at the simple case, then it's a two-strategy case, then for each population that's scalar, and then for the environment again scalar, then you have a three-dimensional system, X, Y, and R. So then the domain, because every state is changing between 0 and 1, then you have a cubic domain from between 0 and 1. And for the cube, you have 8 vertices, right? And those 8 vertices corresponding to 8 isolated fixed point or the equilibrium point. So already you can have 8 equilibrium points in this case. And then if you do the further computation, in the interior of the cube, there is a continuous set of equilibrium. So then that's how you can characterize the equilibrium of the system. And just by simple computation, this is linearization, you can check that the 8 corners, they are not stable. So these are unstable. And then for the interior equilibrium, again, you can check the eigenvalue corresponding to the linearized system. You can compute the eigenvalue, but you have a 0 eigenvalue showing there. And by doing simulations, right, so that's the cube. Right, so then 3 axes is all between 0 and 1. You can see that the system, those are undergoing periodic changes. You can also see from the state against the time axis. You'll see oscillation, periodic solutions. So just through simulations, you haven't done any actual analysis yet. You have this rough idea that let's estimate that, okay, for such a system, oscillation might be very common. So I think that's a piece of exciting news for biologists, because they were always complaining to me, saying, okay, you only look at the equilibrium, but then in the biological system, equilibrium means death. Right? If nothing changes anymore, that's death. For a living system, you obviously changes, but then change are not random. And they are changing maybe periodically over the time of the year or over certain, there's certain mechanism behind that. So they are very interested in looking into those models that can actually produce periodic solutions. So this is one example. Right? After introducing environmental changes, then you can see a periodic solution, not only by simulation, but then the next step is, can you do this by theoretical proofs? So one result you can prove is that so in this idealized, simplified two-population co-evolutionary game model, it have infinitely many periodic orbits in the interior. So that's what we have observed in simulation, and that's what we also want to prove. But then the proof may not be that simple, and does require you to know something from dynamical systems. So one viewpoint is the reversible system idea. So what's a reversible system? Roughly speaking, there's a very rigorous definition in the textbook, but roughly speaking, a reversible system is that if you go forward in time or you go in backwards in time, then the system behave in the same way. So timing going forward or backwards doesn't change the dynamics. It's called a reversible. So in the counter example, in the analysis I gave you in the last part, I said that there is, you remember there's a rock, paper, scissors game. I said that you reverse the matrix A, it's reversing the time of the system, and then all the trajectory will going backwards in time. Right? So then that is an example of reversing in time. But this is a more involved definition of the reversal system. And then one benefit to look into reversible system is that there is a close connection, or there's a very powerful theorem you can use to show the existence of periodic solutions. So that if you know that the orbit intersects with this fixed points of this reversal system present at 2 points, then you know there is periodic solutions. And then luckily, or maybe that's really the reason in the hidden mechanism in our system is that the system model we are working with, that's actually a reversible system. So why is that? So that's our system model. For this system, you can build a mapping. X is still itself, Y is still self, but R, you map it by 1 minus R. And then you can substitute it into this model. You can replace R by 1 minus R. And this part, that gave you a negative sign. You can check it. So actually, so this is actually a mapping. If you go to this task, you see the system itself. So this is, you have constructed such a mapping, and that also means that you prove this is a reversible system. But why? How can we? How do we know that this is a mapping? Where did we get this idea of constructing the mapping to prove it's a reversible system? That's because of symmetry in the system. So that's the cube, right? And then this is a plane. That's R equals 1/2, 0.5. It's like cutting through the whole cube. And then there is another vertical plane there. And the intersection, that is the interior equilibrium point, the continuous set. So the symmetry, the system itself, that inspired us to construct a proof to show the system is a reversible system. So I will not go into details, but once you have such a reversible system constructed, then you can show the periodic solution in the system. Right? So I will not go into detail, but then you can also use your simulation to check the trajectory to show this. Another idea that is called Hamiltonian system theory. So we know that again, doing through some change of variables, there is a reason why we are doing this, because we're seeing that something is conserved as the system evolves. And actually, that's called constant motion. So then this dynamic system, so we, for the system we are working with, we can find the Hamiltonian function for the system that works as, we can check the conditions to show that this actually satisfies this partial differential equations. And then for the Hamiltonian system, the nice property is that you can have level sets. And then the level sets also corresponding to closed orbits. So again, you have a way try to prove the existence of closed orbits or periodic solutions for the system. So that's the second idea. So then we also go in this direction, but this is more general than the reversible system mapping we constructed. So this seems more general, this Hamiltonian system theory idea. So we also try this approach to show the periodic solutions. And the third idea we've tried is a volume preserving property. That's even more general in dynamical systems. So in the system that we worked with, we even work more general than the specific matrix they shown. So we have shown that such a system is volume preserving. So I'm not going to detail, I'm just saying, with all the example I gave are very specific for the PD payoff matrix with the special structure of the R matrix linear structure. But I'm saying if you do allow yourself to look into more generalized multi-population model, then we still have a tool called a volume preserving idea. Use that to show that the system, there is a Louisville theorem, which using a projection of the system and you compute the derivative and divergence of the dynamic system, then you can still showing that the divergence becomes zero and the volume preserving, and then there's a way to show the periodic solutions. Right. Again, just give you the flavor, but don't bother you with all the details. For the two population dynamics model with environmental feedback, what I have shown you is that there's a set of tools from dynamical systems, and I've given you 3 of them. And then they all kind of help you to do the prediction. Right? So if you have feedback introduced into the system, then there can be a periodic solution, and they can be a different type of oscillating behavior. And then you can show using theoretical analysis to prove stuff. So then that's the second topic I covered. And then the last one, just control. So I told you then that the control work is still a bit primitive, but let's show you what we have done. Right? One idea of introducing control action is to look into this imitation rule by the agents. So imitation means I copy those agents I can see, probably in my neighborhood, that are performing better than. Hopefully, they're the best performers. So if I can imitate the best performer, and I can improve my own performance. Right? So then I maximize, I look at everyone around me, their performance, I look at the best one, and then I imitate that. Right? That's the imitation rule. And then one idea of this control is that you offer incentive. So if everyone is mimicking the best performer, and then if somehow you can introduce incentive in the form of a positive number in the payoff matrix corresponding to certain actions. So some action, because of the external control action, can get higher payoff, and then this will have better performance and will propagate in the population. So that's the idea of introducing incentive-based control. But there's a sequence question arise. How much does it cost if you introduce this incentive to make them to converge? I mean, I'm giving the simple example. If everyone is converting to a desirable action A, you make everyone convert to action A. But then you can have uniform incentive, which means everyone, they have the same reward or the incentive in the same payoff matrix, but can be targeted. So I'm not giving everyone the incentive. I'm only targeting those individuals in the population who are most sensitive to the incentive, or they're having critical, strategically important position in the network. Right? Those are targeted individuals. Or if I have a budget constraint, I don't have unlimited money to spend. I have a very limited budget. how can I choose the right target with the right incentive put in there? Those are all different scenarios, different cases in this problem. So for the uniform incentive-based control, then to find the minimum value to convert the whole population. And then again, I'm using the idea. If you remember the first part, I'm talking about threshold model. I'm using the coordinating, anti-coordinating agents. So I'm using the idea there to construct my the proof. So there's an idea called the monotone property. Right? So if someone will do this, take action under a lower incentive, and for sure, it will also do this again with a higher, facing a higher incentive. That's called a monotone property, which turns out to be very important in the proof. And this unique convergent property, that's what I've covered in the threshold model. So using this, we will have a theorem which is saying that if you have all those coordinating agents, if I'm interested in the A strategy, I'm asking them to be A coordinating. And then they also have this monotone property I mentioned. So networks of those A coordinating agents, then they will for sure be A monotone, and they will converge uniquely to a equilibrium. And then so that's one part of convergence. And there's also a part of the result that we have proved that it's possible for one to construct a set which contains the optimal incentive. There is a way to construct this. And then that means if you know there's a finite set contain the maximal optimal solution, then there's different ways to look for the optimal then. I mean, the naive way is to do the binary search. There can be better ways to do this. But nevertheless, within finite steps, you will find that optimal solution. So combining that convergence result and then with this finite time searching result, then you know that it's possible to find optimal incentive R star within finite steps. So that is a nice idea, a nice result. So it's hopeful to look for such an optimal incentive in the control design. And then for the targeted design, it's more complicated. So then the short answer is that is an NP hard problem. So there's no polynomial deterministic algorithm to return you to the result. So you can only approximate what is the optimal result. And in our paper, we looked into very special cases, saying that computationally, if you want to approximate the optimal solution, then you can construct algorithms. And the algorithm works in different scenarios. And then it's even more difficult if you have, we try to have some heuristics, try to find what is the target. And if that target, what's the cost to give the incentive, and then under those incentives, how fast will this converge? But then these are all rely on heuristics. There's no, there may be some bound for the performance, but there's no guarantee to always reach the optimal. We also used simulation to compare the performance of our different algorithms. So I'm almost using up my time. So I just say that the second part of my talk, I look at this replicator dynamics, but I'm also giving, in the beginning, gave this zero determinant strategies. And then that's one way to manipulate the system. And then for the two population system, I introduce environmental feedback. And in the end, very quickly, I mentioned the control. As I said, control is a very open problem for the system. And then for the outlook, so in 2 hours is just not sufficient to cover all the aspects of evolutionary game theory and its potential application to control field. But then we are seeing the emergence of a general framework in this direction. And this, I believe for this summer school, and it's also applicable to a different type of facility networks And then all of you might have your own idea to further extend the model and the work and apply to your own research topic. And then, so these are the references. I just mentioned that. So for the game ideas, we also apply to combine with other population dynamics. So there's a paper in Nature Communications will will appear soon. So our collaboration with marketing people in the population, study population dynamics. And there are also other papers from our group on zero-determinant strategies on periodic solutions of system, and then optimal control of the game dynamics. So feel free to send me emails asking questions if you are interested in reading those references. Thank you so much for giving me this chance to talk about our work.
Thanks. Thanks a lot. It's really, really interesting, and most concept is new to me, especially for the second part. Then for the audience, do anyone have questions? Yeah, probably I could start by one simple question. As a control student, I was wondering, is there any connections between these zero determinant gates and controllability? I would suggest that it doesn't mean that every kind of this reward matrix you can control your opponents to be negative reward.
Sure, yeah, because for the classical controllability idea, that's for linear deterministic systems. And then this system does nonlinear and also does randomized probabilistic system. So then if you look at the model itself, then probably this controllability idea cannot be carried over directly. But the key ideas you have noticed are quite, they share similarities. So then how to manipulate and how to control to a target or to the so then those are similar. So I think some ideas, the definition and the development of those steps can be shared in this study, but you need to do some extra work. So I think that's a very interesting direction to work on.
Yeah, probably yes. And any other questions from the group? I guess most of the idea is too new to really new to most of the audience, so they might need some time to digest and probably need to watch the video again on YouTube. And let's say we can finish this talk, and thank again for Professor Ming Cao to introduce a really new viewpoint of control design, especially for some interaction with environments with other players.
Great. So I will be around in the Gather Town in a few minutes, and I'm free to to continue discussion over there.
Okay. Thank you.
Okay. Bye.